Hello, this is Mr. Coker, and we're going to be covering Module 9 for the Chem II students, and Module 9 has to do with gases. If we go back to Module 2 and remember what some of the properties of gases were, remember that gases consist of small particles moving at a high speed and that they're moving in random directions, that we assume that they have no attractive forces between the molecules. The molecules are very far apart. That plays into the properties of gases. The average kinetic energy of the gas molecules is proportional to their Kelvin temperature. If you double the Kelvin temperature, you double the average kinetic energy. That the particles will be moving in rapidly in constant motion in straight lines until they hit something, and then they'll bounce off and continue to be traveling in straight lines. Gases have pressure, which is due to those collisions. When the particles strike the wall, they create pressure. The symbol for pressure is capital P. The more energetic the collision, the higher the pressure. So generally at a higher temperature, you're going to have more pressure. We measure in the pressure in units of atmospheres, ATMs, or sometimes we use a unit millimeters of mercury, mmHg. Another name for the millimeter of mercury, since it was named after Torricelli, the inventor of the barometer, is we sometimes call the millimeter of mercury a torr. So a torr and a millimeter of mercury are the same thing. Standard pressure is considered to be 1 atmosphere, and that's the same as 760 millimeters of mercury. 60 torr. Now some other quantities about gases you might want to measure. Volume, capital V, typically measured in liters. Temperature, capital T, might be measured in Celsius but converted to kelvins, because you always want Kelvin as your temperature. Remember, to get to Kelvin, you take Celsius plus 273. Standard temperature is 273 Kelvin. And then the amount of gas measured in moles is given the symbol lowercase n. So you might have to convert from grams to moles using your knowledge of how to do that. Looking at some pressure changes, air pressure is going to go down if you go up in altitude. It's also going to go down if the temperature goes down. Barometric pressure or air pressure is simply the weight of the air pushing on something. There are some simple gas laws, and these are the people who derived these to start with. Starting with the oldest, Boyle's law simply shows that pressure times volume is constant, or pressure and volume are inversely related. As one goes up, the other goes down. This is assuming temperature and moles are constant. Boyle's law is usually given as the equation P1V1 equals P2V2. As you can see in the diagram below, when the volume is 4, the pressure is 1. When the volume is 2, the pressure is 2. 4 times 1 is 4, 2 times 2 is 4. Charles looks at the relationship between temperature and volume, showing that temperature and volume are directly related as long as your temperature is in kelvins. If you have only a temperature of 200 kelvins and a volume of 1 liter, if you increase the temperature to 400 kelvins while keeping the pressure in moles constant, the volume will go up to 2 liters. You doubled the Kelvin temperature, you doubled the volume. Gay-Lussac's law, you might have learned in Chem I, this is sometimes called Daltons Law, looks at pressure and temperature, looks just like the Charles law relationship. As temperature goes up, pressure goes up. P1 over T1 equals P2 over T2. Remember, always use kelvins for temperature. Avogadro's law looks at the relationship between volume and moles. V1 over N1 equals V2 over N2. If we could combine these, we could get this law, which is called the combined gas law. Now you might think, well, why would you want a 5th gas law when you have the other 4? But in fact, this one simplifies into the other 4 by simply removing any of the variables that are not variable, but rather are constant. Like if moles and temperature are constant, you've got Boyle's law. If pressure and moles are constant, you have Charles' law. If volume and moles are constant, There you go, Gay-Lussac's law. And if pressure and temperature are constant, you have Avogadro's law, V1 over N1 equals V2 over N2. So the combined gas law simplifies down to give you the other gas laws. Plus, it allows you to vary all the variables, or 3 out of 4 variables instead of just 2. So we've got some questions here to see how you're doing with the concepts. Let's say we start with a cylinder of helium gas, and A or B represents the new volume. What would it look like if the pressure decreases? Would it look like if you started with the initial volume, would pressure decreasing make it look like A, volume would go down, or would pressure decreasing make it look like B, volume goes up? Number 2, what would it look like if the pressure increases? Would increasing the pressure compress it to make it look like A, or let it expand to make it look like B? Jot down your answers for these. We're going to check them on the next slide. And we've got some questions to fill in the blank on. Pressure does what when volume decreases if your moles and temperature are constant? If volume decreases, will pressure increase or decrease? When temperature decreases, volume blank. What does volume do when temperature decreases? C, pressure does what when volume changes from 12 liters to 24 liters? So in other words, when volume goes up, what does pressure do? And then D, volume does what when temperature changes from 15 to 45 Celsius? So if I raise the temperature, what will happen to the volume? Okay, if you jotted down your answers for these, you could check your number 1 should have been B, number 2, A. If you don't agree with those, maybe go back and reread those questions. In other words, slide your slider back to the left and take a look at the previous slide. A, you should have said increases. B, you should have said decreases. C was also decreases. And D would have been increases. Volume increases when temperature increases. We've talked about them in qualitative ways. Now let's talk about them quantitatively. A good way to approach these as math problems is to set up a data table of what you know and what you want to know based on the word problem, and make sure all your temperatures are converted to kelvins, and make sure if you have other units that they match. Like you wouldn't want one volume in milliliters and the other in liters. You wouldn't want one pressure in atmospheres and the other in millimeters of mercury. Then you're going to take the combined gas law, and you're going to figure out what you can leave out because they're constant. You're going to move it around and put it in a form that solves for the unit you want or the quantity you want. Then plug in your numbers of the things that you have and solve for the things that you need to find. Once you have your answer, round off your sig figs and make sure you have the proper units. Let's try this process out. We've got some Freon 12, and we're going to look for what would the new volume be if we had 8 liters at 550 millimeters mercury and we changed the pressure to 2200 millimeters mercury. Of course, temperature and moles are constant. So here's our data table. Got our pressure and our volume, P1, B1, and P2. V2 is our unknown. We don't have to include moles and temperature because they're constant. So that means we just have the Boyle's law, P1, B1 equals P2, V2. We can change it around to get V2 by itself on the one side, and we get V2 equals V1 times P1 over P2. We plug in the numbers from the table, 8 liters times 550 millimeters mercury over 2200 millimeters mercury. We cancel out millimeters mercury, and we get 2 liters. Here we have a volume of oxygen gas of 420 at 18 Celsius. That decimal means there are 3 sig figs in the 420. What temperature will the volume be? 640. So what we know, V1 and V2 are 420 and 640. T1 is 18 Celsius. Make sure it's Kelvin, 291. Solve for T2. Leave pressure and moles out because they're constant. So this is going to be Charles's law. V1 over T1 equals V2 over T2. Using some cross multiplying, we can get T2 by itself algebraically, plug in the numbers we know, cancel out our units, and we end up with 443 Kelvin. Double check the question. Oh, they wanted it in Celsius. So we get that by subtracting 273. 170 Celsius. And the decimal means that the ones place is a sig fig. 0.75 moles, volume 1.5 liters. What volume will 1.2 moles occupy at the same temperature and pressure? This is going to be Avogadro's law, V1 over N1 equals V2 over N2. Because pressure and temperature are going to be left out because they're constant. Solve for the unknown, V2. Plug in the numbers we know. And cancel units. 2 sig figs on everything, so 2.4 liters. Going through these rather quickly, but you can always go back and slow down the video or go backwards in the video to wherever you want to and take a look at these in more detail. Okay, this problem here, here's your pressure, volume, and temperature to start with, and you're solving for the new volume at the new pressure and temperature. You want to make sure you're in kelvins, and you want to make sure your units match, and one of the pressures is atmospheres, the other is millimeters mercury. So let's convert the first pressure to millimeters mercury. Now in this problem, we only have one constant, and that is moles. So this is going to be P1V1 over T1 equals P2V2 over T2. Solving for V2, we get P1V1 T2 over T1 P2. Plug those numbers in from above, cancel out the units, and you get 314 milliliters. So practice this algebra, and there'll be lots of opportunities in the that. We do have another gas law. It's called Dalton's Law, after John Dalton, the guy who is the father of the modern atomic theory, but he also dealt with gases. He said that each gas in a mixture is going to act like it's the only one in the mixture. So the pressure that each gas exerts, which we would call the partial pressure of the individual gas, those pressures are added together to get the total pressure in the container. So you basically just isolate it and say, what would this gas's pressure be? What would that gas's pressure be? What would this other gas's pressure be? Add it up, you'll get the total pressure in the container. So mathematically, it looks like P total equals P1 plus P2 plus P3 plus however many gases you have in the mixture. This might be useful if you're talking about a dive tank for scuba diving. Let's say that your dive tank has 3 gases, 2,850 millimeters mercury of nitrogen, 2,440 millimeters mercury of oxygen, and 750 millimeters mercury of helium. What's the total pressure in the tank? It's just the sum of the individual partial pressures, or 6,040 millimeters of mercury. Now, if one of those was given as atmospheres, I'd convert it to millimeters mercury. If two of them were atmospheres and one of them was millimeters mercury, I'd convert the millimeters mercury to atmospheres. Of course, I would also check what unit they want me to finish in. Okay, do a few more practice problems. Sample of helium, so a certain volume and pressure. What's the new volume if the pressure changes? So that's going to be a P1V1 equals P2V2 problem. Manipulate the equation and get the numbers plugged in. And you have 420 milliliters as the V2. Got a certain pressure at a certain temperature. At what temperature will the pressure increase to the 1140? So P1 over T1 equals P2 over T2. Make sure your temperatures are in kelvins and your pressure units match, which they do. They're both torr. Plug in the numbers you know. Should get 709, which would be kelvins, and then subtract 273 to get the 436 Celsius because the question asks for Celsius. Got some oxygen, 12 liters at 600 millimeters mercury. What's the new pressure when the volume changes to 36 liters? You're tripling the volume, so you should be cutting the pressure down to 1/3. P1 V1 equals P2 V2, P2 equals P1 times V1 over V2, 600 times 12 divided by 36, liters cancel and you get 200 millimeters mercury. The decimal at the end of the zeros tells you that you have 3 sig figs for everything. Got a balloon, certain volume, certain temperature. If the temperature drops, what's the new volume? V1 over T1 equals V2 over T2. Make sure your temperatures are all given in kelvins. Plug in the numbers you know. The new volume is going to go down from 785 milliliters to 729 milliliters. 2 atmospheres at 18 Celsius. What's the new pressure when the temperature is 62 Celsius? Set up your data table. Change everything to kelvins. Solve for the missing variable. Plug in the numbers you know. And you should end up with 2.3 atmospheres. Like I said, I'm going through these quickly, but you can always freeze the video and look at the slides one at a time at your own pace. Okay, certain volume and temperature. At what temperature will the volume be 640? Just T2 equals T1 times V2 over V1, 443 Kelvin, or 170 Celsius. Got a sample of helium, volume of 0.18 liters, pressure 0.8 atmospheres, temperature 29 Celsius. What temperature will the helium have if its volume goes up to 90 and its pressure goes up to 3.2? So it's P1 V1 over T1 equals P2 V2 over T2. We drop out the moles. Solve for T2. And you end up with 604 kelvins, which would be 331 Celsius.